In this video, I'm going to be upgrading the RAM on this ASUS ROG Ally handheld computer, or handheld game console if you want to call it that. Now, up to this point, I've upgraded the RAM on a number of similar devices to this, such as the Steam Deck, which was the first one I attempted this on. I've also upgraded the Lenovo Legion Go, which I ended up actually having some issues with later. But this will basically create the trifecta of these portable x86-based gaming consoles that I will have upgraded the system memory on. Now, just like the Steam Deck and the Lenovo Legion Go, this device comes from the factory with 16 gigabytes of system memory, as you can see right there, and never had any option to upgrade it to anything more. So, what I intend to do in this video is essentially do exactly what I did with those other two devices, and that is install 32 gigs of soldered system memory onto this machine's motherboard. Now, when working on modern electronic devices such as this, a good set of tools is a must-have in order to disassemble and reassemble the device effectively. So when Linus Tech Tips reached out to me and offered to send me their precision toolkit for use in my projects, I definitely had to take them up on the offer. Now, having worked on electronic devices for pretty much as long as I can remember, I've of course used many different toolkits over the years. And after having used this kit for a number of different projects now, I definitely like a lot of the improvements and additions that this kit has over other kits similar to it. Namely, it has a lot of more obscure bits that you don't normally find, such as a quadruple zero Phillips bit, which really helps with small devices like mobile phones, and it's got some game bits up here for use in disassembling some Nintendo devices. Over here, it's got a magnetic tray where you can store your screws from the devices you're disassembling, and the screwdriver itself also has a few improvements, such as the integrated bit storage up here at the handle, which you can use to store 3 of your most commonly used bits. It's got a very free spinning bearing, which is kind of fun to play with, and the magnet in it is a lot stronger than others that I've used. So overall, I can definitely say that this kit works well for my uses, and is definitely a good option for anyone looking for a precision toolkit such as this. You can of course buy it at lttstore.com, and I'll put all the necessary links in the video description. So a huge thanks to Linus Tech Tips for sending this out to me and sponsoring this video. So with that, let's get back to the upgrade. So to begin the disassembly, of course, the first thing we need to do is remove the back cover. And interestingly enough, it looks like the owner of this device, this was sent in to me for repair, installed an interesting looking adapter here to install a full 2280 sized NVMe SSD in a slot meant for a 2230 SSD. So it definitely is a little bit janky, as you can see right there, but I mean, I guess it works just fine. It didn't seem to have any problems, so I'm just going to leave that alone. So now we just need to proceed and remove the rest of the components to get the motherboard out of the chassis. Alright, so as you can see here, we've got the motherboard successfully removed, and the RAM should be right under this tape here. And yep, there it is. And as you can see, it's actually got Micron RAM on it, and specifically that is part number, let's see if we can read that, yeah, D8BCW. So those should be, I believe, 16 gigabit chips each, or sorry, 32 gigabit chips each, which of course make up a total of 16 gigabytes and with all 4 together. So with that all taken apart, now we just need to get the board on my little board preheater and then begin the process of desoldering each of these 4 chips. Alright, so with the board all warmed up on the preheater here, the first thing we need to do is apply some flux to each chip. And actually, before I do that, I'm going to remove this piece right here to make sure it doesn't have any problems or get in our way while we're working here. There we go. So now we can apply some flux to each chip and then begin the removal process. Now temperature wise, I'm going to heat these up at around 330 degrees Celsius on the hot air, and the board preheater itself is set to its maximum setting, which is 250 degrees Celsius. So I'll go ahead and get the hot air warming up here and begin the process of removing each RAM chip. Now as you're heating these, you want to carefully tap each one, and when it starts to move very easily from tapping, just very light taps, that is when it's ready to come off the board. Alright, and now with all 4 chips removed, now all we need to do is remove all the residual solder. And to do that, I'm going to use my soldering iron with some solder wick. But first I'm going to apply some flux to each one, just a little bit of extra. Make it a little bit easier for us here. And then we'll just remove the solder. Alright, and now with all the residual solder removed, we can clean off all this burnt flux using some rubbing alcohol and a paper towel. And now with all the flux cleaned, we can now prepare the new chips to be installed onto this board. Alright, so I got the new chips out here, and these chips are actually the exact same chips that I used to perform this exact upgrade on the Steam Deck. They actually use the exact same chip. These are the exact same part number. So you can see right there, they are Samsung K3L KC0BM chips right there. Let me see if I can zoom in there. Yeah, you can probably read that part number right there on the top of that chip. So yep, these are the exact same chips that I used to perform the 32 gig upgrade on the Steam Deck. So with these laying out here, the first thing I want to do is flip them all over. And if you take a close look at them, you can see that they already have solder applied, and in fact the solder they have on them is leaded solder, so that'll make our job way easier than if they were pre-balled with lead-free solder. But first I'm just going to apply a little bit of flux to each one, just a little blob in the middle. And then with that applied, I'm going to take them and heat each one on the board preheater to melt that flux around all the pads. Alright, so with the board preheater out here, I'm just going to take each one and heat it on top of it. So just hold it like this until the flux melts, and then I'll kind of rotate the chip back and forth. And as you can see, now the flux is between most of the pads there. And when we solder it, it'll go through all of them, but as it is now, that's enough. You don't want to put too much on these, or it'll be hard to solder them because they'll try to float away on you. And with that all done, we can get the board back up here and solder them onto it. Alright, so now with the board up to temperature, the first thing I'm going to do is apply some more flux, just a little bit. And with that applied, we're just going to take each chip, align pin 1 to the corner right here with the little mark. And luckily this board has a silkscreen outline around each one, which makes alignment very easy. And with the chips all aligned, we can now take the hot air and solder each one into position. And just like that, all 4 chips have been successfully soldered. So now what I want to do is get this board reinstalled into the chassis just temporarily, test it, make sure it still boots with this new RAM installed, and then we will proceed with the rest of this mod, which involves editing the system BIOS. So with that, I'm going to get this assembled and we'll give it a test. Alright, so as you can see here, I've gotten the device assembled as much as it really needs to be. However, with ASUS devices, there is one thing you have to be very careful of when you're testing devices like this, and that is this ambient light sensor located right here. Now, it might not look like much, but you see this component surrounded by this black piece of foam here? That is an ambient light sensor, and what that does is when the bottom case is removed, as it is now of course, and this sensor has light being shined in it, the machine will act like it's completely dead. And I've worked on one of these before, and that actually got me and threw me for a loop when I was working on it, because I could not figure out why it wouldn't charge or turn on. So what you can do is what I'm going to do right here and cover it with a piece of black tape. So with that piece of tape installed, no light is able to hit that sensor, therefore the machine should turn on without issue. So let me go ahead and finish the assembly here. So I'm going to plug the battery in. So go ahead and plug that SSD adapter in there, install the SSD, and it looks like I'm going to have to screw that down. Can't say I'd really recommend this adapter, it's kind of janky. Anyway, it's in now, so now let's just go ahead and turn the device over and see if we can power it on successfully. Okay, I might need to apply some power to it first. Okay, it's definitely taking some power, so let's see if we can turn it on now. There we go. And it hasn't posted yet, despite having a logo on the screen. That logo is actually programmed into an EEPROM on the screen itself, so it actually shows an image when you first power it on, even before it posts, which is kind of weird and kind of something you have to look out for with these modern devices. And yep, there we go, it posted. That's good. Very good sign. Okay, and it was able to boot Windows without any problem. So let's go ahead and log in here. Okay, now let's head on over to the settings and see what we've got here. So yep, as I expected, it only detects 16 gigabytes of RAM still. Now, as I mentioned earlier, to finish this mod, we actually have to modify the system BIOS. And the reason for that is because these x86-based systems have what's called SPD, or Serial Presence Detect data, hard-coded into their system BIOS to tell it how much system memory is installed. And in order to get a machine like this to detect more installed soldered memory, we have to go in and modify those SPD data entries in the system BIOS. So I'll show you exactly how I'm going to do that now. Now, before we actually begin modifying the BIOS itself, we have to get a copy of the BIOS to modify. And in order to do that, we have to take out the motherboard once again, desolder the system's SPI ROM, which of course contains the system BIOS, dump it with an EEPROM programmer, and then edit it on a computer. So I'm going to get this board back out of the chassis, and then I'll show you the full process of dumping and modifying the system BIOS. Alright, so with the board removed and back on the preheater once again, we can now begin the process of removing the SPI ROM, which is of course located right here. So just like before, I'm just going to start by applying some flux, and then simply use hot air to desolder it from the board. And now with the EEPROM removed, we can now put it in the EEPROM programmer and dump it. Alright, so with the EEPROM now removed, we are now ready to begin the process of dumping and modifying it. So in front of me here, I've got everything that's going to be needed for this. Of course, first you need an EEPROM programmer, and I'm using a TL866, but you can use pretty much anything you want. However, one thing you want to be aware of is that this EEPROM that is on this machine's motherboard is actually a 1.8 volt EEPROM. So you have to make sure the programmer you're using supports 1.8 volt EEPROMs. And if it doesn't, you'll have to use something like this, which is a level shifter, which will allow you to use a 1.8 volt EEPROM in a programmer that only supports 3.3 volts. Now, if you actually try to put this EEPROM without this level shifter in a 3.3 volt programmer, you have the potential of damaging it. So of course, I would not recommend doing that if at all possible. The last thing you'll need here is an adapter for this specific package of EEPROM. And this is optional. You can, of course, solder wires and stuff to it to make it work, but this just makes it a whole lot easier. So what I'm going to do is I'm going to go ahead and put the EEPROM in it, just like so. Just open the lid and it goes right in like so. And then you just put that in the EEPROM programmer just like that. So over here on the computer, you can see I've got the software open, and the first thing that needs to be done is you need to actually select the model of EEPROM that you're working with. Now, for some reason, this XGeiku software doesn't actually have the definition for this specific EEPROM in it, so I'm using one that's very close to it, but not the exact part number. In this case, that is MX25U25645G. I believe this one would also work just the same way, but as long as the package type is the same and the density, in this case 256 megabit, is correct, you should be good to go. So I'll go ahead and select that here. And with that selected, we can go ahead and attempt to read the content of it. And as you can see here, it fails on the ID check, and that is, of course, because we're using a definition for a slightly different chip. So to get around that, we just need to uncheck check ID right here, and then we can read one more time. And as you can see now, it's reading successfully. So I'll go ahead and wait for the dump to complete, and then we will proceed with the modifications. Alright, and with the dump complete, let's just go ahead and take a look at it and make sure it actually dumped some data. And yep, it sure did. So now we can go ahead and save that. I'll just save it into this directory here, and we will save it as ROG orig.bin for original. Go ahead and save that. And with that saved, we now want to open that dump in a hex editor. Let's go ahead and open it up here. And with that open, we want to go through and search for a specific string. So let's go to find here, and what we want to search for is APCB, so just the text APCB. And this should give us every position in the file where an APCB file is located. So we can see that's not it there. Go ahead and search again. That's not it either. And yes, this is it. You can see there is an entry of SPD data there with a memory part number in it, and you can see there's a whole bunch of them in a row there. So what we want to do now is we want to find the end of this section. So let's go ahead and just scroll down a ways here, and we want to select that entire section up until the next blank section there. And we'll just copy that, create a new file, and paste it in there. And with that done, let's go ahead and save this as ROG APCB orig.bin, just to keep another backup there. And now what we want to do is locate a piece of SPD data to use as the base for our edited data. Now, one thing you can use to easily search for a piece of data is this set of bytes right here, 0200480000. And if I go ahead and copy that, go up to the top of the file and search for that, go to hex values, we'll paste that in. That will give us the very beginning of each piece of SPD data. So you can see right there, after these zeros, that's where the data starts, this 231113. We search for that again. You can see there's the next copy, and so on and so forth. So we want to keep that in mind when we're working on this file, which I'll show you what we'll need that for in just a minute. But let's use this piece of data as our base here. You can see the part number is extremely similar to the chips we are using. However, instead of KC0BM, this one is KB0BM. Now that is just the exact same chip, but the smaller version of it, so the 32 gigabit version of the chip instead of the 64 gigabit version that we installed. So this will be a good point to use as the base for our SPD modifications. So let's go ahead and find the beginning of that once again using that string, or that set of bytes. And there we go right here, so we know the beginning of the data is right there. So with that in mind, we now need to reference the SPD specification for LPDDR memory, which I've got open right here. And there's 2 bytes that we need to modify to make this work. The first byte is byte 6, which is SDRAM package type. And essentially we need to change this from 2 dies per package to 4 dies per package, because that is one of the differences between the smaller version of this chip versus the larger version. So in order to do that, I'm actually going to open the calculator here, put it in programmer mode, and we can actually use this to edit each individual bit. So to begin, we need to find byte 6 in our SPD data. So to do that, we just go in here. You know, this is byte 0, so 0, 1, 2, 3, 4, 5, 6. So you can see that is 95, so let's just type that in as a hex value here, 95. And if we go over to our reference once again, you can see that bits 6 through 4 here, or 4 through 6, however you want to call it, describe this particular parameter here. So we need to change this from 2 dies per package to 4 dies per package. So we just need to change bit 5 from 0 to 1. So we can go 0, 1, 2, 3, 4, 5, change that to 1, and you can see our resulting value is B5. So with that in mind, we just go over here and edit it accordingly. So we type B5 in there, and that's one piece of data successfully modified, or at least 1 byte of that data. So now we need to modify the next byte, and that is actually byte 12. So there it is right here. You can see that this describes the organization, and what we need to change is we need to change this value from 1 package rank to 2 package ranks. So you can see that would correspond to bit 3. We need to change that from 0 to 1. So we need to first get the original bit here. So we're on bit 6, or byte 6 rather, 7, 8, 9, 10, 11, 12. You can see that's currently set to 02. Put that in the calculator. And you can see right there what our settings are. So let's go over here once again. We need to change bit 3 from 0 to 1. So that's this bit here. And that becomes A. So let's go ahead into the file again and change this to 0A. And that should be all the modifications that need to be made. But now what we need to do is we need to copy this piece of SPD data to every entry of SPD data. And the reason for that is because there could be strap configurations on this logic board. You did see that we actually took micron RAM from it. So chances are these straps are going to be set appropriately for one of these micron settings rather than the SPD data for these Samsung memory chips here. So what we want to do is simply just copy everything we changed here, and in fact the entire piece of data here. So just the first part of it there is all you need, up to this 04 before all these zeros here. We're just going to go ahead and copy that, and then we're going to locate and replace each instance of SPD data with our modified data. So once again we can use this search value here to find it. You can see right there. Go ahead and paste right to overwrite that. Find again. That's the data we already modified. Overwrite that, and so on and so forth. Alright, and that is every piece of SPD data modified, as you can see right there. So now we'll go ahead and save this as, we will save it as APCB mod. And now we are ready to proceed with the final modification, and that is fixing the checksum. So you can see here I've got a script in here called man edit apcb checksum fix.py. So in order to use that, I'm going to start by opening up command prompt here, and we're going to change into this directory here. And what I'm going to do is simply run Python 3. I believe this is a Python 3 script. If it's not, I'll try it with regular Python. The path to that file, and then ROG apcb mod.bin, ROG apcb mod fixed.bin and go ahead and run that script. So it is Python, not Python 3. And there we go. You can see it successfully updated the checksum in that file. And we can actually verify that if we go ahead and open it and compare it with these two. You can see that this byte right here has changed. So now with that all done, we now need to copy the updated checksum file back into our source file. So go back over and copy that. I just did Control A, Control C on that. Let's verify one more time. And now we need to just overwrite all this data. So we'll just start at the beginning here, select paste right, and now we can save this once and for all. So we'll save that as rog modded.bin, and we are now ready to write that file back onto the EEPROM. So let's go ahead and load that in the EEPROM programmer software here, rog modded, and go ahead and write it to the EEPROM. Alright, so as you can see here, the EEPROM was successfully written, so now we just need to reinstall it back onto the motherboard. Alright, so before I reinstall the chip, the first thing I want to do is actually remove all this lead-free solder and replace it with leaded solder, just to make it a lot easier to install and remove later if needed. So go ahead and get the soldering iron warmed up here and remove and replace all of that solder. And that's looking good there, so we're now ready to reinstall the EEPROM. And just like that, the EEPROM is now reinstalled. So now all that's left to do is fully reassemble the system and give it a final test. Alright, so now with the device mostly reassembled here, I am going to leave the back cover off just in case I need to go back in there for any reason and put this tape back over the sensor here. But with that all done, we should be able to power it on, and in theory it should just work and now detect 32 gigs of installed memory. So let's get it powered on right now. So just like before, I'm going to power it on with USB-C connected. Make sure we get some voltage and current being pulled through there. And yep, that all looks good. So let's go ahead and power it on. Okay, the screen's on, so now we just have to wait that excruciatingly long time for it to actually post. And yes, it posted. That's a really, really good sign. And we're in Windows. Let's go ahead and log in. And moment of truth here. Yes! There it is! 32 gigs of installed system memory. So let's see if we can go into Task Manager and just verify that there. Yep, look at that. 21.8 gigs of usable memory. We're running at 6,400 mega transfers per second, just like we were before. And yeah, you can see actually the total up in that corner right there, 32 gigs is available and working. And I don't know what Task Manager just did there. There we go. Yeah, you can see 32 gigs with 27.7 gigs usable, and everything seems to be working as expected. So with that all done and working, there is one last thing we need to take care of in order to prevent BIOS updates from being inadvertently installed onto this machine, which of course will overwrite the changes we made to the BIOS just now. So the first thing I'm going to do here is go into Device Manager and we want to look for firmware, or system firmware. I forget exactly what it's called. Let's see. Yeah, firmware right there. And you see this device called system firmware? That is actually what Windows uses to detect and interface with the system BIOS to read data from it, such as its version, and of course use that to determine if any updates are available through Windows Update. Which, by the way, updating the BIOS through Windows Update automatically is a terrible idea. I would never trust Windows to automatically install BIOS updates of all things, knowing how unreliable it tends to be. So in order to disable this, and of course this will only pertain to the specific install of Windows that's currently running on this system, but in order to disable firmware updates, all we need to do is select Disable Device on the system firmware entry here. And in theory, once that's done, Windows Update will no longer be able to query the system firmware version and therefore not be able to update the system BIOS. So, with that all taken care of, that should in theory be a fully upgraded and fully working system. So, that has been the successful upgrade of this ASUS ROG Ally handheld PC from 16GB to 32GB of system memory. So with that, I hope you enjoyed this video.